Hi everybody. All right, we're going to look in this video at an example of exponential growth. This does appear in the book as example 15.3, but we'll be working through it on paper, and I've reproduced the text of it for you here. So, basically, the example is about population, and population is a natural real-life application of exponential functions, at least initially. And the reason is that I said in the previous video, an exponential function has this character, which is that the bigger it is, the faster it grows. The rate of growth is proportional to the size. And in a population, for example, if you have a population with 1 million people and you think about how many babies could be born that year in, say, a year's time, well, you're going to get a lot more than if you had a population over only of 100 people. Right? A population of 100 people, if that 100 people was all couples and each couple had a baby, that would be 50 new babies that year. Whereas in 1 million people, if the same thing happened, you would get 500,000 new babies that year. So the increase in a year's time would be greater if the population is greater. This is sort of a suggestion of why we think of population as being an exponential type of growth. Another characterization of exponential growth is that the amount either grows or shrinks by the same amount every year. So if the population doubles the first year and the growth is exponential, it will double the second year. If the population grows by 1/3 the first year, it will grow by an additional third the next year, and so on. All right, so let's look at an example. Here we're talking about the population size of a country was 12.7 million in the year 2000, and 14.3 million in the year 2010. So just to record these, this is like the year, and this is the population. Now, the year is 2000. The population was 12.7, and I'm just going to keep that number as 12.7 and keep track of the units as being in millions of people. So in the year 2000, the population was 12.7. In the year 2010, the population was 14.3, also million. And part A of the question says, assuming that we have an exponential growth for the population size, find a formula for the population depending on the year t, where t, the number t, t is very commonly used for time. We're going to be using that instead of x in this equation, where t equals 0 in the year 2000. So, of course, we could measure time just by the year itself, use t equal 2000, but it's going to simplify our lives to take their suggestion and say that in the year 2000, the time t is equal to 0. And that means that in the year 2010, the time t is equal to, well, it's been, in that case, 10 years since the year 2000, so it must be the time t is equal to 10. And what we're going to do is use these as our inputs, and these as our outputs of the population. So the sort of the initial information that we're given about the population. If the population is an exponential function, well, if it's an exponential function, we know that it's equal to c times b to the x. Here, instead of using x as our independent variable, we're going to be using t because it's time. And if we reinterpret it in those terms, then what we get is our function f of x, that's the population, except it's going to be f of t, is equal to c times b to the power t. And in order to get a formula for this population, we just need to figure out what are c and b. This is very similar to the problems we did in the previous video. Okay. And what do we know? Well, f of t is equal to c times b to the t. This is annoying. Let me just fix it for you so it looks proper. It's f of t. We also know that at time 0, the population is 12.7 million. And so we would write that at f of 0, the t is 0. we get 12.7, and the units are millions of people. And we also are given that, let's see, f of 10, that is at time equal 10 years, the population is 14.3 million. And what are we asked to figure out here? Well, we're asked to find a formula for the population. Yeah. That basically just means fill in the numbers C and B in this formula. That's going to be our formula. And then we're asked to use the following. Use this model to predict what is the population size going to be in the year 2015, assuming the formula holds then. And how long will it take for the population to reach 18 million? You could think of this population, 12.7 million. That's like 1.5 New York cities, something like that. And so we could imagine a big urban area, a little bigger than New York City. That could be this population. And here's how it grows over the course of 10 years. It goes from 12.7 million up to 14 million. So it adds like 1.5 million people in 10 years. And we want to know how much will it have added by the year 2015? And also, how long is these numbers is it going to take for these numbers to reach all the way up to 18 million? Okay. If you're doing something like city planning, like you're trying to design the infrastructure for your city going forward, do you have enough power and water? Do you have enough streets? Do you have enough room for development of housing and so on? Then this is the kind of projection of population is extremely important. So this is something that has real world application. Okay. So let's go ahead and talk about it. Here's how we're going to do it. We're going to do it just like the way we did before. We have our formula f of t is c times b to the t, and we're given these two inputs and outputs. We're going to start with the first one. The first one, f of 0, the input is 0, and that's handy because it is going to be really easy when we plug it in. We're going to plug in 0 for t, into this formula, into the function. 0 is going to go in for t, and f of 0 is all going to be replaced with that 12.7. So we have that 12.7 is equal to c times b to the 0. Now, the nice thing is that c times b to the 0 is just equal to 1. And because of this, we get that 12.7 is equal to c. And I mentioned in the last video, if you're given in an exponential function, if you're given the value of the function when the input is 0, that value of the function is just going to be that number that's multiplied in the front, that value c. Okay. So we're halfway done with finding our function already. The next thing that we need to do is plug in our second point. Let's go ahead and do it. Here we're going to plug in the input of 10, the output of 14.3, so 10 is going to go in for t. 14.3 is going to go in for f of t. It's what the whole thing will be equal to. And then we've also determined the value of c, so we're going to put this 12.7 in for c. Let's see. Let's plugging in, we get 14.3 is equal to, c is 12.7, and it's times b to the power 10. All right. This is an equation that has just one variable in it. It looks messy. Don't let the decimals scare you, because we're just going to deal with those with a calculator in the end. And until that point, we're just going to treat them just like any other numbers. So first, we have a number. We're trying to get the b by itself. We have a number in front of that b to the 10 power, and we're just going to get rid of that by dividing both sides by it. So we divide by 12.7 on both sides. On the right-hand side, these cancel. I'm going to leave the left-hand side as just 14.3 over 12.7, and that's equal to b to the power 10. And now, the way that we cancel off a 10th power is we take the 10th root, or the 10th radical of it. So that's let me do it in another color so it's clear what we're doing here. We're going to take the 10th root of that side and the 10th root of that side. And what we get on the right is just b. That's great because we've gotten our base b by itself. And on the right-hand side, we have the 10th root of 14.3 over 12.7. Now, I want to plug this into a calculator. It may help you when plugging in to note that the 10th root, you can also write that as that fraction, whatever's inside, to the power of 1 over 10. So this is, alternatively, we could say that b is equal to 14.3 over 12.7 to the power 1/10. So either way is fine. Let's go ahead. We're going to put this into Desmos and see what we can get. 14.3 over 12.7 to the 1/10 power. So 14.3 divided by 12.7. And then, let's go like that instead. There we go. And we're going to go to the power, and then up in the power, in parentheses, I'll put 1 divided by 10 to get a 1/10 power. And you'll see that 14.3 over 12.7 to the power 1/10 is equal to, in the gray box in the computation there, it's equal to 1.0119. And I'm going to round that off to the third decimal place and make it 1.012. Let's go over. Oopsie. So this thing, our number b, is approximately equal to 1.012. So altogether, what is the formula that will determine the population? The population is given by the formula f of t is equal to, the constant in front is 12.7. That's our c in the front. So 12.7 times our base to the power t, and our base is 1.012 to the power t. And this is the answer to part A. This is a formula that gives the population at any particular time. Okay. So we've answered now part A. Find a formula for the population depending on the year t. Here's our formula. Formula f of t is 12.7 times 1.012 to the t. Next. What will the population size be in the year 2015, assuming the formula holds until then? So this is part B. What is the population in 2015? Well, in 2015, if we're going to use this formula, we need to plug something in for t, for time, and we just need to know the value of t that corresponds with 2015. And since t is the number of years where t equals 0 is 2000, then in 2015 we have that t is equal to 15. And so what do? We just substitute f of 15. And what is it equal to? It's equal to 12.7 times 1.012 to the power 15. How do we calculate this? Well, in a calculator, you could raise this number 1.012 to the power 15. That's going to be some decimal. And then we multiply the result by 12.7. And that will give the answer in millions of people. Now, what I'm actually going to do is in Desmos, just because this might be helpful to us later, I'm going to go ahead and just put this entire function in Desmos. Let's go ahead and see what it looks like. 12.7, 1.012. So let's see. This is f, parentheses, f of t. What is it equal to? It's equal to 12.7 times, and then in parentheses, 1.012. Of course, we could get greater accuracy by using more decimals in that base b. I'm going to leave it there for now, although I think that's a reasonable objection. Stick in more decimals for greater accuracy. Okay, here's a function. And then if we want to plug a number into that function, here. In fact, you can you can zoom out and you can see this function here when x is 0, you can see up it crosses the y-axis at, well, 10, 11, it's between 12 and 13. In fact, it's 12.7. And at 10, it's managed to make it all the way up to 14.3. And what this is asking is, at 15, what has it reached? So let's go ahead and see what is... The reason this is sort of worth taking the time to put this into Desmos is that we can now use the function notation f of 15, and it gives us right away f of 15 is 15.18837. I'm only going to take 2 decimals for population, 15.19. So this thing is equal to 15.19 million people in 2015. So this is our answer, our solution for part B. What is the population in 2015 of the city? It will have grown to 15.19 million. Okay. Finally, part C, when will the population reach 18 million, assuming that this model still continues to hold? So let's take a look. When will it reach 18 million? Well, the population, of course, is not given by t. T, the time, that's what we're trying to find. What we're trying to figure out is for which t do we get that f of t is equal to 18 million? So we want to find what is the correct t to put in. And what we're going to do is we're going to use our formula. Here's the formula, again, for the function. And we know what we want the output to be, and we're trying to find the t. So we're just going to replace the output, that f of t, with 18, and then leave the rest of it in there with the t. And that'll give us an equation with t as an unknown. All right, so that looks like 18 is the output, and that's equal to 12.7 times 1.012 to the t. Let's double check we've got our formula correct there. Looks good. Okay. And what we want to do is find t. That is to say, we're trying to find at what time does the population reach 18? Does it equal 18? What t do we have to put in there in order to make the right-hand side of this equation, when you calculate it out, turn into 18? And here's how we're going to do it. Don't let the decimals intimidate you. Just treat them as though they were any other number. And the way that we're going to start is by getting rid of this guy. He's a number multiplied in front. And we can get rid of it by dividing both sides by 12.7. So what are we going to get on the left? We're going to get to 18 over 12.7. And on the right, when we divide by 12.7, 12.7 cancels, and we just have 1.012 to the power t. Okay, now we have a slightly annoying problem, which is we want to get t by itself, but t is not down here. T is up in the exponent. And so we can't use the same taking a radical or a root here because we don't know what radical or root it is. That's the t that we're looking for. So instead, the way that we deal with solving equations where there's a variable in the exponent is we use logs. We take the log of both sides, and you can, once again, use any logarithm you like. You can use the log in any base b and take it on both sides. However, I would recommend using either the special log, log in base 10, or special log in base e. So this is just as a recall. When we write log of x, what we mean is the log in base 10. And when we write the natural log of x, what we mean is the log in base e. So those tend to be the two log buttons on all standard calculators, so it's sort of helpful to work with one of those. You can use either one that you like. I'm going to go ahead and use the natural log. Take natural log of both sides. Here we go. So we're taking this equation, and we're going to take the natural log of both sides. So we have the natural log of the left, which is 18 over 12.7. And that's equal to the natural log of the right, which is natural log of 1.012 to the t. Now, the reason this helps us is that we have this rule of logs, which says if you have a natural log or any log of something to a power, you can take the power and bring it out in the front and multiply. So we keep the left-hand side the same, ln 18 over 12.7. And on the right, we get t times ln of 1.012. Now, on the right-hand side, there's only one variable, that's t, and this other part, natural log of 1.012, this is just equal to a number. It looks messy. You could get a decimal approximation of it by plugging it into a calculator, but it's a number. And so ultimately, we want to get t by itself, and it's connected to this number by multiplication. So we're going to solve that by dividing both sides. We're going to divide here by ln of 1.012. and divide here by ln of 1.012. On the right-hand side, whatever the number, natural log of 1.012, whatever that is, it's the same number on top and bottom, and it's not equal to 0 as long as this is not equal to 1 inside. So the natural log of any number except 1 is not 0. We don't have to worry, and that means that we can cancel it. On the right-hand side, we're only left with our number t. And on the right-hand side, we've got, well, it's a little bit of a mess. It is the natural log of 18 over 12.7 divided by the natural log of 1.012. This will give us the time t, and remember the time is number of years since the year 2000. So we're going to see to reach 18 million, I'm going to guess it's going to take about 25 years to reach 18 million, but that's just a guess. Let's see. Natural log of 18 over 12.7 divided by natural log of 1.012. Let's see if we can plug this into Desmos. So here we have natural log of 18 over 12.7 divided by the natural log 1.012. And altogether, it tells me it's going to take 29.238. So let's call that 29.24 years. Here we go. That is our value of t. So this t is equal to 29.3. What was it again? Let's see. 29.24. So for part C, we found the value of t. T is 29.24, but it always helps to do a reality check. What is the question asking? The question is asking, when will the population reach 18 million? Well, it will reach it when t is equal to 29.24, and that's going to happen so population reaches 18 million in the year 2029. 2020, it's 29.24 years, so it's sometime between the beginning of 2029 and the beginning of 2030. And that's really our final answer for this question. When does it? Is in the year 2029. All right, that's it for this problem. I'll see you in the next one.